What kind of sounds might exist in space? Maybe you're thinking, sound cannot travel in a vacuum. But that doesn't mean the universe is silent. Actually, the universe is filled with all kinds of vibrations. Through a technique called data sonification, scientists can convert plasma waves, radio waves, and even gravitational wave data into sounds we can hear. Today we will delve into and hear some of the most intriguing sounds in the universe. From the ghostly murmur of a passing comet to the deep roar of a supermassive black hole. The echo left behind from black holes that collided 5 billion years ago. There's a famous saying, in space, no one can hear you scream. And that's essentially true. Sound as we know it needs a medium to travel, and space is largely a vacuum. There's no medium for conventional sound waves to propagate through. However, there are other kinds of fluctuations in the universe. Radio waves, plasma waves, and even gravitational waves can be converted through data sonification into signals that we can perceive as sound. Our first stop is relatively close to Earth, Saturn. Its rings are made up of countless ice grains and rock fragments. Most of these particles become charged through ionization by solar radiation. At the same time, Saturn's magnetosphere is filled with freely moving charged particles. These particles interact with each other, forming complex plasma phenomena. And they're not static. When charged particles in Saturn's rings interact with the plasma in the magnetosphere, they are influenced by the Lorentz force. This force causes charged particles to spiral along magnetic field lines, generating oscillating waves within the plasma. These are known as plasma waves. In 1997, NASA launched the Cassini probe specifically to study Saturn and its system up close. One of its key tasks was to explore Saturn's rings and the interactions within its complex plasma environment. While flying through the rings, Cassini's radio and plasma wave science instrument recorded the fluctuations generated by these particles. This instrument was incredibly sensitive, capable of detecting lightning activity in Saturn's atmosphere, even from thousands of kilometers away. Inside Saturn's thinnest rings, some dust particles are only about 200 nanometers wide, roughly the size of a virus. When this fine dust hit the instrument sensors, it instantly created tiny bursts of plasma. And these plasma signals could be converted into sound data. This allowed scientists to effectively hear the intricate electromagnetic interactions occurring deep within the magnetosphere. And when that audio data is played back, it sounds eerie, almost otherworldly. But that's not even the most amazing part. In 2017, during one of its final orbital maneuvers, near the end of its mission, Cassini captured another striking recording. These were plasma waves traveling the magnetic field lines between Saturn and its active moon, Enceladus. This recording is particularly poignant because it was essentially one of Cassini's final gifts or transmissions. Just 2 weeks later, the probe's remarkable 20-year mission concluded as it was directed to plunge into Saturn's atmosphere, vaporizing completely. This might have been the last echo it sent back across the void. But Cassini wasn't the only probe sending back the sounds of the cosmos. In 2014, the European Space Agency's Rosetta spacecraft returned an even more stunning space recording. The source of the data this time was a comet that had been roaming the edges of our solar system for billions of years. Our second stop, Comet 67P Churyumov-Gerasimenko, the primary target of the Rosetta mission. It is also the only comet to date onto which humanity has successfully landed a probe. The comet orbits the Sun approximately every 6.5 years. Its nucleus holds primitive material left over from the early stages of the solar system's formation, dating back over 4.5 billion years. One of Rosetta's main objectives was to study how the solar wind interacts with the comet's coma and tail. Therefore, scientists equipped the Rosetta spacecraft with a suite of plasma detection instruments. These included a Langmuir probe for measuring the surrounding electron density and plasma oscillations, and a magnetometer to detect magnetic field perturbations caused by plasma waves. Collectively, the fluctuations in this data painted a picture of the dynamic plasma environment surrounding the comet. However, detecting such waves wasn't entirely novel in itself. Scientists had previously detected magnetic waves around several comets, including the famous Halley's Comet. So what made Comet 6-7P special? The answer lies in the unique sound it generated. The sound signature from 6-7P was completely different from that of any previously studied comet, suggesting unique physical processes were at play. And here's where it gets really interesting. The sound could actually be analyzed and broken down into different components. There's a rhythmic clicking component, reflecting periodic fluctuations in plasma density within the coma and perturbations of the comet's own magnetic field due to the solar wind. And a low background hum revealed continuous, low-frequency oscillations within the plasma environment. Let's listen to it again. Our third stop takes us to something truly mind-bending: black holes. Have you ever wondered what a black hole might sound like? Fasten your seatbelts, because we're about to find out. Departing from Comet 6-7P, Churyumov-Gerasimenko, we travel about 240 million light-years to the center of the Perseus galaxy cluster. At its heart lies a supermassive black hole. Supermassive black holes, like this one, are often surrounded by incredibly hot accretion disks, with temperatures reaching millions of degrees Celsius, emitting intense X-rays. NASA's Chandra X-ray Observatory, orbiting high above Earth, is a space telescope, specifically designed to detect these high-energy X-rays. Equipped with highly sensitive detectors, it converts X-ray photons from deep space into digital signals. This allows scientists to map the distribution of features like black holes, supernova remnants, and hot gas within galaxy clusters. In 2003, Chandra captured a stunning dataset from the Perseus Cluster. Through high-resolution imaging and spectral analysis, scientists studied the X-ray emissions from the central black hole and the dynamics of the surrounding hot gas. In 2022, researchers revisited this X-ray data and applied data sonification techniques, converting the observed pressure waves in the cluster gas into audible sound. In doing so, they essentially uncovered the deepest note ever detected, propagating through the universe. It's a B-flat note approximately 57 octaves below middle C. The actual period of this sound wave is incredibly long. A single oscillation takes about 10 million years to complete. This frequency is far too low for human ears to perceive directly. Therefore, scientists used sonification techniques to scale the frequency up by quadrillions of times, bringing it into the audible range for humans. The result is a deep, eerie rumble, enough to send shivers down your spine. The scientific significance of this sound goes far beyond its eerie quality. Perhaps most importantly, it reveals a potential impact on the evolution of galaxy clusters themselves. Galaxy clusters contain hundreds or even thousands of galaxies bound together by gravity. The space between these galaxies isn't empty. It's filled with a vast, thin, extremely hot gas, or plasma known as the intracluster medium, ICM. While incredibly diffuse, this ICM is actually denser and much hotter, millions of degrees, than the interstellar medium found within galaxies like our own Milky Way. One leading hypothesis suggests that these sound waves, propagating outwards from the central black hole, carry energy into the intracluster medium, helping to keep it hot. This ongoing energy transfer prevents the gas from cooling down too quickly, which in turn regulates star formation within the cluster's galaxies. This implies that the sound emanating from the supermassive black hole may play a crucial, albeit invisible, role in shaping the large-scale evolution of the entire galaxy cluster. Our fourth stop involves a technological achievement that even Albert Einstein himself doubted was possible. If he could witness today's discoveries in this area, he would surely be amazed. In 1916, based on his theory of general relativity, Einstein predicted the existence of gravitational waves. Think of them like ripples spreading out on the surface of a pond when you throw in a stone. Except, instead of rippling water, gravitational waves are ripples in the very fabric of spacetime itself, causing it to stretch and squeeze on an incredibly tiny scale as they pass. However, Einstein initially believed these effects would be far too minuscule for humans ever to detect directly. Yet, just over a century later, humans have not only successfully detected gravitational waves, but have also established a global network of observatories. This network allows for multi-point observations and cross-validation of data, helping to pinpoint the source and direction of incoming gravitational waves. If you're not familiar with how these detectors operate, the principle is quite ingenious and might surprise you. Unlike traditional optical telescopes that use lenses or mirrors to collect light, these detectors use lasers. Scientists shoot laser beams down two long perpendicular arms, typically several kilometers in length. When a gravitational wave passes through Earth, it immediately stretches and squeezes spacetime, causing subtle changes in the lengths of these arms, and thus the travel time of the laser light. To be clear, this change in length is incredibly small, less than 1/10,000th the diameter of a proton. Yet, by precisely measuring these minuscule changes, the detectors record the signature of a passing gravitational wave. The frequency of the detected gravitational wave determines the characteristics of the sound produced when the data is sonified. This allows us to effectively hear cosmic events like colliding black holes. Different types of black hole collisions produce distinct sounds. The merger of less massive black holes often results in a lower-pitched, longer chirp sound that increases in frequency towards the end. Collisions involving more massive black holes tend to generate shorter, sharper signals, often at lower frequencies overall. The sound you might hear could represent the gravitational waves from two black holes that merged billions of years ago. So while conventional sound doesn't travel in a vacuum, if we learn to listen using scientific instruments and techniques like sonification, we find the universe is composing a grand and mysterious symphony all around us. By finding the right methods, we can begin to capture these hidden voices echoing across the cosmos. Thank you for watching. Don't forget to like, share, and subscribe for more space adventures.